So, thank the organizers and thank Professor Wang's introduction. My name is Xin Guo, and I'm from the Hong Kong Polytechnic University. So my research focus on learning theory, so that's the theoretical analysis of machine learning algorithms. And the work I present today is a little bit different from the mainstream research, and it's like but it's more applied and more closer related to data. So this is like a weekend project, and I have before everything, I want to acknowledge the generous support by RGC Hong Kong and my collaborators, Professor Chiang, who is an assistant professor in University of British Columbia, who got his PhD degree from Duke, with the supervisor of Professor Land. And I met them when I was doing a postdoc in Duke, and this is like a weekend project. So they introduced me the background and data, which I still don't understand completely, but I got the mathematics in front of that, and we did the collaboration. It turns out recently that the work was published in a very prestigious journal on the sociology side, so which makes me feel like I should present it somewhere. So in real applications, many data has the count data nature, which means they're more naturally represented by count by positive non-negative integers than by real numbers. For example, if we study the frequency of alcohol drinking, study some other sociology problems like campus bullying, like drug usage, and many other applications. Most recently, we are interested in this research, which studies the network size estimate of social network, and the data was collected by questionnaire, and my friend told me that each interviewee is first paid money and then ask a question to fill a questionnaire. So at the first page of the questionnaire, they're asked the question, say, how many would you please read the first name of your close friends, which means if you really have troubles, you would be able to talk with. Then after they fill in the first name, and they're asked many questions like their areas of residence and their job, and what's the nature, and what content do you have connections with them. So in short, that's many questions. And after the interviewee filling all those blanks, and they're asked with another probe, like, is there anyone else? And then another nightmare comes, and the interviewee need to fill all the other informations of the second close friend they know. And the maximum friend name they are allowed to fill in is 5, and after 5 the interview simply stops, because interviewee fatigue, and we all know that at some stage people get tired and bored about those questions. So in this application, the data structure of the number of friends takes the form of 0, 1, 2, 3, 4, 5, and 6 plus, because at the stage of 6 6 or more, we simply stop at that number. Another example is also related to network size estimation, where people are asked how many people know in a neighborhood which are close enough, in the sense that if you have really troubles, if you're going to travel, and would you like to park your pets to them, and would you willing to ask them picking up mail for you, ask them or help them watering plants, and so on and so forth. So those are the standard defined close friends. And in this questionnaire, the number of friends are categorized into 4 categories: 0, 1 to 5, 6 to 10, and 11 or more. So we see that in many research and applications designed to collecting those data, the questionnaires are designed to with some categories. So the numbers are grouped into some categories. Those are strongly depend on the domain experts, and today I'm still asking my friend, would that be scientific? But that's a common practice, and sometimes depends on how precise the interviewee want to provide their data, and whether would the interviewee can precisely remember what they want, the number they want to input. So many different and complex factors. So still, the grouped and the right sense and form of data collection is a wide and common practice. We all know that if you want to model some mechanism, the data is generated by a person. So I somehow feel like if they want to model the mechanism of data generation with person, what they really want to do is to find the average, and but they don't have some other distribution looks better than Poisson. Or, I mean, the real world is complicated, so that's just a model. But anyway, statistically, if you want to model some count numbers from Poisson distribution, then we all know that to estimate this unknown parameter lambda, the maximum likelihood estimator is the average of all the numbers you have, and asymptotically we have some normal distribution. Here, this I lambda is the Fisher information of that model. And what we mean by grouped and right sensor data means that you don't have direct access to those xi's, but you only have yi's, which are numbers of or indexes of your groups. Here, what I mentioned about group is some successive non-negative integers from 0 to infinity. So we have a grouping scheme which contains n, capital N groups. The first group starts from 0 to L2 minus 1, and the second group starts from L2 to L3 minus 1. The last group starts from Ln to infinity. And the unknown but integer, like the background integer xi, is observed through yi, which equals j if and only if xi belongs to the j's group. So the group, but the probability, if we model the underlying mechanism by Poisson model, the probability of the ith group is ij, which is the summation of those Poisson probabilities. This is the likelihood where we replace this j by the observed yi. And we compute Fisher information, which is here this derivative is the derivative of those theta j with respect to lambda. So some observations about this Fisher information. First, when n equals 1, that's really a trivial case where we group all the non-negative integers in the same group. And you may imagine that the data you have is only 1, 1, 1, 1, in which sense all the information is lost, and which does not make any sense. Starting from 2, which might be a little bit surprising, which is that the ij, the Fisher information, start to become positive, which means we can consistently recover lambda through data as the sample size tends to infinity. And the Fisher information has another good property, which is if script G prime is the refinement of script G, which means we cut one or more groups into some smaller groups and put it back into the scheme. And then the Fisher information is strictly increased and it's always increased and strictly increased. And because of the model is very smooth and every function is infinitely differentiable, then we all know that if you make this maximum likelihood estimator on those model, the lambda hat would have a asymptotic normal distribution with with the variance, the reciprocal of the variance related to proportional to the feature information. So mathematically speaking, if you have more groups, and then the feature information could be larger, which means you have a more efficient algorithm. But otherwise, if you insist on grouping the data into smaller number of groups, then you suffer from a smaller feature information. And usually in applications, my feeling is that people are quite flexible with how the integers are grouped, but quite parsimonious with how many, at most, how many groups we can use. So we set the restriction that the maximum group number could be bounded by n0 and try to maximize the feature information by adjusting the grouping scheme. Here we define an object function, which is the feature information multiplies the density of some prior distribution of the unknown parameter lambda, which could be concentrated on some specific point if some pilot study is done and lambda 0 is the output of the pilot study. But to maximize such an object function, we need to try infinitely many grouping scheme, even though we restrict the number of groups to be n0. By the way, if we want to maximize this object function, G must achieve n0 because if we do refinement, we can always improve feature information. So we introduced a three-step M algorithm which can guarantee to obtain the global maximum. The first step is to select the big enough integer m. The m is related to the computational complexity, so if it is too large, we suffer from some longer time of computation. But we find that selecting an initial guess of m, which is close to the guess of the lambda, is helpful. And the first step is that we compare and maximize omega p, the object function, among all the grouping schemes, such that their last group covers the big integer m. And in the last step, we find an upper bound of the feature information among all the grouping schemes that the last group does not cover m. So we see that the grouping scheme we consider in the second and the third category putting together form all the possible grouping schemes we can ever take. But now we need to find, in the third category, we need to find an upper bound instead of really compute the maximum possible values, because there are infinitely many grouping schemes where the last group does not cover m. And so we use a graph to demonstrate the step we consider about this algorithm. So here in our example, m equals 4, and so the number of groups we set is 3. So we see that in picture A, we have listed all the possible grouping scheme where the last group covers the integer m. In the second graph, we list apart a very small proportion of the grouping schemes which the last group does not cover the number m. And we do an operation on the second set. This set has infinitely many grouping schemes, and we list only 6 here. we do an operation on this set of grouping scheme by first we merge all the groups that happens after the number 4. So we merge them into a single group. Then we cut all the numbers which are larger than the number m into a single group. So then all the possible grouping scheme in the second category would for all the possible grouping schemes in the category B, we can find some grouping scheme in the category D. Of course, D is not practical and it's hypothetical, but for any single grouping scheme in B, we can find a grouping scheme in D, which is the refinement of that group. And more importantly, the total number of grouping schemes in D is finite. In our example here, it covers only 4 different grouping schemes, which is quite practical to implement. So we simply compute all the Fisher information of all the grouping schemes in the category 4, and as an upper bound of the Fisher information in the group B. And the group A and B adding together form all the possible grouping schemes we can employ. So this comes from an intuition that the last group as the leading number in the last group tends to infinity, the last group would provide less and less contribution to the Fisher information. So when it is too large, that grouping scheme can be ignored. The advantage of the algorithm is that we may false reject some true optimal grouping scheme, but once we have this flag, which is that the upper bound is less than or equal to the maximum object function value in category 2, it is guaranteed that this optimizer found is the global maximizer. And then we consider the zero inflated Poisson case, which was motivated by the over-dispersion phenomenon, which because for Poisson distribution, we all know that its mean equals variance. So, but for real data, it's widely observed that these two quantities are not equal. And people may use zero inflated Poisson, which adds some concentration on the point 0, or use some other tool like negative binomial regression and odd quasi-likelihood. But zero inflated Poisson is one such approach motivated by this over-dispersion phenomenon. Here, the Fisher information becomes a matrix because we have the zero inflated parameter and also the Poisson parameter. For this, then we have the definition of the object function is tricky because we can because the order in the matrix space is only a partial order. So we define such so those definitions are widely already extensively studied in the area of experimental design, and we require that they satisfy some isotonic property with respect to the loner ordering, which is if two matrices have the relation that A minus B is positive semi-definite, then the score function must satisfy that SA be less than, greater than or equal to SB. So all these 3 optimality criteria satisfy this isotonic property. And we see in literature some people are trying to compare which is better than the other, but as from the mathematical perspective, I don't really see any specific difference. That's simply 3 animals, and it's hard to say which one is better than the other. So again, when n equals 1, all the information is lost. But when n equals 2, now because we have 2 parameters, So when n equals 2, the determinant of the Fisher matrix equals 0, which means it's impossible to simultaneously estimate lambda and p. A little bit surprisingly, when n is 3 or more, the Fisher information's determinant is positive, which means the estimation of these two parameters can be consistent. And we also have the property that if G prime is a refinement of G, then the difference of the Fisher information matrix between that of G prime and G is positive semi-definite. So with the score function, we enjoy that the score must at least be no smaller. And in this case, we do integral and plug in the score function outside of the integral to define this object function. Because the input and the output of this object function is the same as the previous one we studied with Poisson distribution, so the previous M algorithm can still be applied to this object function here. Here are some computational examples, and we have implemented the algorithm into an R package and released into the R CRAN R package repository called GRC data, where in this first example, we generate some prior distribution where we are using Poisson model. Only the lambda has a probability of half to stay at the point 4 and 5 respectively, and we see that with one iteration, the code successfully find the optimal grouping scheme. In the second example, we study some continuous prior distribution of a truncated normal. Here, the normal on lambda has mean 3 and standard deviation 1, truncated at the point 1 and between 1 and 10. We use the Poisson model, and we use the numerical integration method. We find that the algorithm still can compute the optimal grouping scheme quickly. Then, in the third example, we studied the zero inflated Poisson case with some quite general prior distribution on both p and lambda. So, in this case, because of the numerical integral, so the time takes longer, about 4.5 seconds on a desktop computer. Then we studied the last case here is when lambda has half probability to be on 15 and 17, and we study Poisson model, but we study the case that we're taking 8 groups, and it turns out that the algorithm has 4 iterations. Each one means we reach at some stage where the upper bound on the third category is larger than the maximum in the second category. So we have to start over. So we have started over 3 times, but it costs only less than 3 seconds on my desktop computer, with the maximum M reaches to 27. On this slide, we show that some existing, as I mentioned, people are now the research about making such experimental design is really arbitrary. People just freely set someone, but this process cannot be done scientifically. Like in one paper we read recently, the reference means the reference grouping scheme, and after the lambda is obtained, we tried the optimal grouping scheme found by our code with the same number of group as the reference, and we find that the standard error could be reduced. And we also tried some other optimal grouping scheme with much less number of groups, and we find that we still can achieve a smaller standard error, which means the process in literature, the study of the grouping scheme design could really be improved with a large margin. So that's all of my talk. Thank you.
Okay, maybe time for one question. Okay, so if no question, let's thank the speaker again.